Question 1. An electric dipole with dipole moment 5 times 10 to the power minus 6 km is aligned with the direction of a uniform electric field of magnitude 4 times 10 to the power 5 Newton divided by c. The dipole is then rotated through an angle of 60 degrees with respect to the electric field. The change in the potential energy of the dipole is. Correct answer is option D. The potential energy of an electric dipole in a uniform electric field is given by U equals P cos theta, where P is the dipole moment, E is the electric field, and theta is the angle between them. Now let us consider dipole potential energy. The potential energy of a dipole in an electric field depends on the orientation of the dipole with respect to the field and is expressed as U equals P cos theta. Initially, the dipole is aligned with the electric field, so the initial angle is theta I equals 0 degree. After rotation, the final angle is theta F equals 60 degree. The change in potential energy is delta U equals UF, UI equals P cos theta F plus P cos theta I. This simplifies to delta U equals P cos theta I, cos theta F. Substituting the given values, P equals 5 times 10 to the power minus 6 km, E equals 4 times 10 to the power 5 Newton divided by C, cos 0 degree equals 1. And cos 60 degree equals 1 divided by 2. Therefore, delta U equals 5 times 10 to the power minus 6 times 4 times 10 to the power 5, 1 minus 1 divided by 2. Simplifying, delta U equals 20 times 10 to the power minus 1 times 1 divided by 2 equals 1 joule. Hence, the change in the potential energy of the dipole is 1.0 joule. Question 2. Two identical charged conducting spheres A and B have their centers separated by a certain distance. Charge on each sphere is Q and the force of repulsion between them is F. A third identical uncharged conducting sphere is brought in contact with sphere A first and then with B and finally removed from both. The new force of repulsion between spheres A and B is best given as. Correct answer is option B. The electrostatic force between 2 point charges is given by Coulomb's law F equals kq1 q2 divided by r squared. Now let us consider Coulomb's law. According to Coulomb's law, the force between 2 point charges is proportional to the product of the charges and inversely proportional to the square of the distance between them. Initially, both spheres A and B carry charge Q. Therefore, the initial force is F equals kq squared divided by r squared. When the identical uncharged sphere C touches sphere A, the charge distributes equally. Thus, charge on A becomes Q divided by 2 and charge on C becomes Q divided by 2. Next, sphere C with charge Q divided by 2 touches sphere B which originally has charge Q. The total charge becomes Q plus Q divided by 2 equals 3Q divided by 2. Since the spheres are identical, the charge distributes equally. Hence each sphere receives 3Q divided by 4. Therefore, sphere B has charge 3Q divided by 4. Finally, the charges on spheres A and B are Q divided by 2 and 3Q divided by 4, respectively. The new force is F equals K divided by R squared left, Q divided by 2 times 3Q divided by 4 right, equals 3 divided by 8 kq squared divided by R squared. Since F equals kq squared divided by R squared, we obtain F equals 3 farad divided by 8. Hence, the new force of repulsion between spheres A and B is 3 farad divided by 8. Question 3. A metal cube of side 5 cm is charged with 6 C. The surface charge density on the cube is. Correct answer is option D. The surface charge density is defined as sigma equals Q divided by A, where Q is the total charge and A is the surface area. Now let us consider surface charge density. Surface charge density represents the amount of electric charge per unit area distributed over the surface of a conductor. The side of the cube is 5 cm, which is equal to 0.05 meter. The area of one face of the cube is 0.05 squared equals 0.0025 meters squared. Since the cube has 6 faces, the total surface area becomes A equals 6 times 0.0025 equals 0.015 meters squared. The total charge on the cube is Q equals 6 mu C equals 6 times 10 to the power minus 6 coulomb. Substituting the values into the formula, sigma equals frac 6 times 10 to the power minus 60.015. This gives sigma equals 4 times 10 to the power minus 4 coulomb m to the power minus 2. Therefore, the surface charge density is 4 times 10 to the power minus 4 coulomb m to the power minus 2 equals 0.4 times 10 to the power minus 3 coulomb m to the power minus 2. Question 4. The value of electric potential at a distance of 9 cm from the point charge 4 times 10 to the power minus 7 coulomb is given 1 divided by 4 pi var epsilon 0 equals 9 times 10 to the power 9 Newton m to the power 2 coulomb to the power minus 2. Correct answer is option D. The electric potential at a distance r from a point charge q is given by V equals 1 divided by 4 pi var epsilon 0 q divided by r. Now let us consider electric potential of point charge. The electric potential due to a point charge is equal to Coulomb's constant multiplied by the charge and divided by the distance from the charge. Given Q equals 4 times 10 to the power minus 7 coulomb, R equals 9 cm equals 0.09 meter, and 1 divided by 4 pi var epsilon 0 equals 9 times 10 to the power 9. Substituting into the formula, V equals 9 times 10 to the power 9 times frac 4 times 10 to the power minus 70.09. First calculate the numerator. 9 times 10 to the power 9 times 4 times 10 to the power minus 7 equals 36 times 10 to the power 2. Thus V equals 36 times 10 to the power 2 divided by 0.09. Since 36 divided by 0.09 equals 400, we obtain V equals 4 times 10 to the power 4 volt. Hence, the electric potential at the given distance is 4 times 10 to the power 4 volt. Question 5. A thin spherical shell is charged by some source. The potential difference between the 2 points C and P, in V, shown in the figure is, take 1 divided by 4 pi var epsilon 0 equals 9 times 10 to the power 9 psi units. Correct answer is option D. For a uniformly charged thin spherical shell, the electric potential at any point inside the shell, R, is constant and equal to V equals kq divided by R. Now let us consider potential inside spherical shell. Inside a uniformly charged spherical shell, the electric field is zero and therefore the electric potential remains constant throughout the interior region. In the figure, both points C and P lie inside the spherical shell of radius r equals 3 cm. Therefore, the potential at point C and point P are the same and given by V equals kq divided by r. Thus Vc equals Vp. Hence the potential difference is Vc, Vp equals 0. Therefore, the potential difference between points C and P is 0. Question 6. Given below are two statements, one is labeled as assertion A and the other is labeled as reason R. Assertion A: the potential, V, at any axial point, at 2 meter distance, R, from the center of the dipole moment vector P vector of magnitude 4 times 10 to the power minus 6 km, is plus or minus 9 times 10 to the power 3 volt. Take 1 divided by 4 pi var epsilon 0 equals 9 times 10 to the power 9 psi units. Reason R, V equals pm2p divided by 4 pi var epsilon 0 r squared, where r is the distance of any axial point situated at 2 meter from the center of the dipole. Correct answer is option A. The electric potential at a point due to an electric dipole is given by V equals 1 divided by 4 pi var epsilon 0 p cos theta divided by r squared, where p is the dipole moment and r is the distance from the center of the dipole. Now let us consider electric potential due to dipole. The potential due to a dipole depends on the orientation of the observation point. For axial points, theta equals 0 degree or 180 degree, so the potential becomes V equals pmp divided by 4 pi var epsilon 0 r squared. For axial points, cos theta equals plus or minus 1. Therefore, the potential becomes V equals plus or minus 1 divided by 4 pi var epsilon 0 p divided by r squared. Given p equals 4 times 10 to the power minus 6 km, r equals 2 meter, and 1 divided by 4 pi var epsilon 0 equals 9 times 10 to the power 9. Substituting the values, V equals plus or minus frac 9 times 10 to the power 9 times 4 times 10 to the power minus 6, 2, squared. This gives V equals plus or minus 36 times 10 to the power 3 divided by 4 equals plus or minus 9 times 10 to the power 3 volt. Thus, assertion A is correct. Reason R states the expression V equals plus or minus 2p divided by 4 pi var epsilon 0 r squared, which is another equivalent form of the dipole potential expression for axial points. Therefore, both assertion A and reason R are true and the reason correctly explains the assertion. Question 7. According to Gauss' law of electrostatics, electric flux through a closed surface depends on. Correct answer is Gauss' law states that the total electric flux through any closed surface is equal to the charge enclosed divided by the permittivity of free space, phi equals frac inside of air epsilon 0. Now let us consider Gauss' law. According to Gauss' law, the electric flux through a closed surface depends only on the total charge enclosed by the surface and does not depend on the shape or size of the surface. From the relation phi equals frac inside of air epsilon 0, the electric flux depends only on the charge enclosed within the closed surface. The electric flux does not depend on the area, shape, or volume of the surface. Therefore, the electric flux through a closed surface depends only on the quantity of charge enclosed by that surface. Question 8. A charge QC is placed at the center of a cube. The flux coming out from any one of its faces will be, in SI unit. Correct answer is option D. According to Gauss' law, the total electric flux through a closed surface is given by phi total equals Q divided by var epsilon 0, where Q is the charge enclosed by the surface. Now let us consider Gauss' law. Gauss' law states that the net electric flux through any closed surface depends only on the total charge enclosed inside the surface. A cube has 6 identical faces. When a charge is placed at the center, the electric flux distributes equally through all 6 faces due to symmetry. Therefore, the flux through one face of the cube is phi face equals 1 divided by 6 times Q divided by var epsilon 0 equals Q divided by 6 var epsilon 0. The charge is given in microcoulombs, so Q mu C equals Q times 10 to the power minus 6 coulomb. Substituting this conversion, the flux through one face becomes phi face equals Q divided by 6 var epsilon 0 times 10 to the power minus 6. Hence, the electric flux coming out from any one face of the cube is Q divided by 6 var epsilon 0 times 10 to the power minus 6. Question 9. If a conducting sphere of radius r is charged, then the electric field at a distance r from the center of the sphere would be V equals potential on the surface of the sphere. Correct answer is option. The electric potential on the surface of a charged conducting sphere is given by V equals kq divided by r, where q is the total charge on the sphere. Now let us consider potential of conducting sphere. For a charged conducting sphere, the potential on the surface is equal to the potential of a point charge placed at its center. The electric field at a distance r, outside the sphere, is given by E equals kq divided by r squared. From the potential expression V equals kq divided by r, we obtain kq equals Vr. Substituting kq equals Vr into the electric field expression gives E equals Vr divided by r squared. Therefore, the electric field at distance r from the center of the sphere is E equals Rv divided by r squared. Question 10. An electric dipole is placed at an angle of 30 degrees with an electric field of intensity 2 times 10 to the power 5 Newton c to the power of 1. It experiences a torque equal to 4 Newton m. Calculate the magnitude of charge on the dipole, if the dipole length is 2 cm. Correct answer is option. The torque experienced by an electric dipole in a uniform electric field is given by τ equals P sin theta, where P is the dipole moment. Now let us consider torque on electric dipole. An electric dipole placed in a uniform electric field experiences a torque that tends to align the dipole with the field direction, and the torque magnitude is given by τ equals P sin theta. The dipole moment is defined as P equals Qd, where Q is the charge and d is the dipole length. Given τ equals 4 Newton m, E equals 2 times 10 to the power 5 Newton c to the power minus 1, theta equals 30 degree, and d equals 2 centimeter equals 0.02 meter. First find the dipole moment using P equals τ divided by E sin theta. Substituting the values, P equals 4 divided by 2 times 10 to the power 5, sin 30 degree. Since sin 30 degree equals 1 divided by 2, we obtain P equals 4 divided by 2 times 10 to the power 5, 0.5, equals 4 times 10 to the power minus 5 km. Using P equals QD, the charge is Q equals P divided by D equals frac 4 times 10 to the power minus 50.02. Thus Q equals 2 times 10 to the power minus 3 km equals 2 mc. Hence, the magnitude of charge on the dipole is 2 mc. Question 11. If point SE vector dot ds vector equals 0 over a surface, then correct answer is option D. According to Gauss' law, the net electric flux through a closed surface is given by phi equals point E vector dot ds vector equals frac inc var epsilon 0. Now let us consider Gauss' law. Gauss' law states that the total electric flux through a closed surface is proportional to the net charge enclosed within that surface. If point E vector dot ds vector equals 0, then from Gauss' law the enclosed charge must be 0. This means that the net flux through the surface is 0. Therefore, the total number of electric field lines entering the surface must be equal to the total number of field lines leaving the surface. Hence, the correct statement is that the number of flux lines entering the surface is equal to the number of flux lines leaving it. Question 12. An electric dipole is placed as shown in the figure. The electric potential, in 10 to the power 2 volt, at point P due to the dipole is, equals permittivity of free space and 1 divided by 4 pi var epsilon 0 equals K. Correct answer is option D. The electric potential due to a point charge is given by V equals KQ divided by R, where K equals 1 divided by 4 pi var epsilon 0 and R is the distance from the charge. Now let us consider electric potential of point charge. The potential at a point due to multiple charges is obtained by algebraic addition of potentials due to each charge. From the figure, the distance of point P from the positive charge plus Q is 2 cm and from the negative charge minus Q is 8 cm. Thus the potential at P due to plus Q is V underscore plus equals KQ divided by 2 times 10 to the power minus 2. The potential at P due to minus Q is V underscore equals KQ divided by 8 times 10 to the power minus 2. The net potential is obtained by superposition, V equals V underscore plus V underscore. Therefore V equals KQ divided by 2 times 10 to the power minus 2, KQ divided by 8 times 10 to the power minus 2. Simplifying, V equals k left, 1 divided by 2 times 10 to the power minus 2 minus 1 divided by 8 times 10 to the power minus 2 right. This gives V equals k left, 4 minus 1 divided by 8 times 10 to the power minus 2 right, equals KQ3 divided by 8 times 10 to the power 2. Hence the electric potential at point P is 3 divided by 8 QK times 10 to the power 2. Question 13. 6 charges plus Q, minus Q, plus Q, minus Q, plus Q, and minus Q are fixed at the corners of a hexagon of side D as shown in the figure. The work done in bringing a charge Q to the center of the hexagon from infinity is, equals permittivity of free space. Correct answer is option B. The electric potential due to a point charge is given by V equals 1 divided by 4 pi var epsilon 0 Q divided by R. The net potential at a point due to several charges is obtained by algebraic addition of the potentials produced by each charge. Now let us consider electric potential of point charge. Electric potential is a scalar quantity, therefore potentials due to different charges add algebraically. Let us examine superposition principle. In a regular hexagon, the distance from the center to each vertex is equal to the side length d. Each charge is located at the same distance d from the center of the hexagon. Therefore the potential at the center due to a single charge Q is V equals 1 divided by 4 pi var epsilon 0 Q divided by D. There are 3 charges plus Q and 3 charges minus Q placed alternately at the vertices of the hexagon. Thus the total potential at the center is V0 equals 1 divided by 4 pi var epsilon 0 D. Plus Q minus Q plus Q minus Q plus Q minus Q. The positive and negative contributions cancel exactly. Hence the net electric potential at the center becomes V0 equals 0. The work done in bringing a charge Q from infinity to a point with potential V is given by W equals Q0, V0 minus V underscore infinity. Since the potential at infinity is 0 and the potential at the center is also 0, W equals Q0, 0 minus 0. Therefore the work done in bringing the charge to the center is 0. Question 14. 2 hollow conducting spheres of radii R1 and R2, R1, R2, have equal charges. The potential would be. Correct answer is option B. The electric potential of a conducting spherical shell carrying charge Q is given by V equals 1 divided by 4 pi var epsilon 0 Q divided by R, where R is the radius of the sphere. Now let us consider electric potential of conducting sphere. For a conducting sphere, the electric potential on the surface is inversely proportional to its radius. Both spheres are given equal charges Q. Thus the potentials of the two spheres are V1 equals 1 divided by 4 pi var epsilon 0 Q divided by R1 and V2 equals 1 divided by 4 pi var epsilon 0 Q divided by R2. Since R1, R2, the radius of the first sphere is much larger than the second. Therefore V propto 1 divided by R. A larger radius gives smaller potential, and a smaller radius gives larger potential. Hence the potential of the smaller sphere is greater than that of the bigger sphere. Question 15. 2 point charges minus Q and plus Q are placed at a distance L, as shown in the figure. The magnitude of electric field intensity at a distance r, RL, varies as. Correct answer is option B. For distances much larger than the separation of charges, RL, the system of charges minus Q and plus Q behaves as an electric dipole. Now let us consider electric dipole. An electric dipole consists of two equal and opposite charges separated by a small distance. Let us examine far field of dipole. At points far from the dipole, RL, the field behaves as the field of a dipole. The electric field due to a dipole at a distant point is given by E equals 1 divided by 4 pi var epsilon 0 2 p divided by r cubed, where p is the dipole moment. The dipole moment is defined as p equals ql. Substituting p equals ql into the expression gives E equals 1 divided by 4 pi var epsilon 0 2 ql divided by r cubed. Thus the magnitude of the electric field varies inversely with the cube of the distance. Therefore E propto 1 divided by r cubed. Question 16. Polar molecules are the molecules. Correct answer is option A. Polar molecules possess a permanent separation between the centers of positive and negative charges. Now let us consider polar molecules. In polar molecules, the centers of positive and negative charges do not coincide. Let us examine permanent dipole moment. This separation of charges produces a permanent electric dipole moment even in the absence of an external electric field. Because of this charge separation, the molecule behaves as a permanent electric dipole. Therefore, polar molecules have a non-zero permanent dipole moment. Hence, polar molecules are defined as molecules having a permanent electric dipole moment. Question 17. A dipole is placed in an electric field as shown. In which direction will it move? Correct answer is option. In the given arrangement, the electric field is non-uniform. The magnitude of the electric field near the plus Q charge is greater than that near the minus Q charge. Now let us consider electric dipole in non-uniform field. In a non-uniform electric field, the forces acting on the two charges of a dipole are not equal. Let us examine force on dipole. The charge located in the stronger field experiences a larger force. Let the electric field near plus Q be E and near minus Q be E, where E. The positive charge experiences a force in the direction of the electric field, while the negative charge experiences a force opposite to the field. Since the force on plus Q is larger, the resultant force on the dipole acts towards the right. A physical system naturally moves in the direction where its potential energy decreases. Therefore, the dipole moves towards the right so that its potential energy decreases. Question 18. Two charged spherical conductors of radius r1 and r2 are connected by a wire. Then the ratio of surface charge densities of the spheres, sigma 1 divided by sigma 2, is. Correct answer is option. When two conducting spheres are connected by a wire, charge redistributes until the electric potentials of both spheres become equal. Now let us consider potential of conducting sphere. The electric potential of a conducting sphere is given by V equals 1 divided by 4 pi var epsilon 0 Q divided by R. Let us examine charge redistribution. For two connected conductors in electrostatic equilibrium, their potentials are equal. Let the charges on the spheres after connection be Q and Q. Since the potentials are equal, Q1 divided by R1 equals Q2 divided by R2. Thus Q1, Q2 equals R1, R2. The surface charge density of a sphere is given by sigma equals Q divided by 4 pi R squared. Therefore sigma 1 equals Q1 divided by 4 pi R1 squared and sigma 2 equals Q2 divided by 4 pi R2 squared. Taking the ratio, sigma 1 divided by sigma 2 equals Q1 divided by Q2 times R2 squared divided by R1 squared. Substituting Q1 divided by Q2 equals R1 divided by R2, we obtain sigma 1 divided by sigma 2 equals R2 divided by R1. Hence the ratio of surface charge densities is sigma 1 divided by sigma 2 equals R2 divided by R1. Question 19. A short electric dipole has a dipole moment of 16 times 10 to the power minus 9 cm. The electric potential due to the dipole at a point at a distance of 0.6 meter from the center of the dipole, situated on a line making an angle of 60 degrees with the dipole axis is 1 divided by 4 pi var epsilon 0 equals 9 times 10 to the power 9 nm squared divided by c squared. Correct answer is option A. The electric potential at a point due to a short electric dipole is given by V equals 1 divided by 4 pi var epsilon 0 p cos theta divided by r squared. Now let us consider electric potential due to dipole. Here P is the dipole moment, R is the distance from the center of the dipole, and theta is the angle between the dipole axis and the position vector. Given dipole moment P equals 16 times 10 to the power minus 9 cm, distance R equals 0.6 meter, and angle theta equals 60 degree. Substituting into the formula, V equals 9 times 10 to the power 9 times frac 16 times 10 to the power minus 9 cos 60 degree, 0.6, squared. Since cos 60 degree equals 1 divided by 2, the expression becomes V equals 9 times 10 to the power 9 times frac 16 times 10 to the power minus 9 times 1 divided by 20.36. Thus V equals 9 times 8 divided by 0.36. Therefore V equals 200 volt. Question 20. In a certain region of space with volume 0.2 meter cubed, the electric potential is found to be 5 volt throughout. The magnitude of electric field in this region is. Correct answer is option D. The electric field is related to electric potential by the relation E vector equals nabla V, which means the electric field is the negative gradient of the electric potential. Now let us consider electric field and potential relation. Electric field represents the rate of change of electric potential with respect to distance. In the given region, the electric potential is constant and equal to 5 volt everywhere. Therefore the gradient of potential is 0. Since E equals dV divided by dr, differentiation of a constant potential gives 0. Hence the magnitude of the electric field in this region is 0.